Let's now take a look at standardising our normal distribution. Because remember, our table of values was all for the standard normal distribution. So we'd like to convert our data into that. So Z, our standard normal distribution, we said was when we have an average or a mean of 0 and a variance of 1. And that was the formula we ended up with for the probability density function. How did we get there? Well, I'm going to do some transformations of our bell-shaped curve. If I was to get Z and divide it by the deviation, what does that do in graphing? Well, that's a dilation, and it would be horizontal by a factor of sigma. So I've dilated it by a factor of sigma. But it would become, so I've changed the Z to Z on sigma, so now the power you'll see is Z squared on 2 sigma squared. But the problem with doing that is when we stretch it, we're going to change the area under the curve. And remember, we want the probabilities all to be 1 and so on. We need that area to always be 1. Let's just imagine it's a rectangle to make life easier than the curve. So base times height would have to equal 1. But I've just stretched it. I want the area to be 1. However, because of our dilation, we've made the area now whatever that sigma is. Now I want it to be 1. So to correct it, now I'll do a vertical dilation of 1 on sigma. That will then, in our area function, it will turn out now to be 1 again, because now the sigmas cancel out. I'm back to base times height, basically. And I'll get that. So now I do my dilation on the y values as well. That will stretch it vertically by 1 on sigma. Therefore, I'll change my function and substitute in. And then finally, what we're going to do here is shift it to the right, because I want to get that average to 0. So I'm going to move the mean to 0. And we now get that. We have, you'll see on the right hand side here, that is what we said our probability density function for a normal distribution was. Do not panic too much about how I got there. You don't need to know that. But this is where it comes from, and that's why we do this x minus mu over the deviation. That's how we'll do it. So that is what we call our z-scores, and that is our standardisation equation. We get whatever the value is, subtract the mean, divide it by the deviation, and that becomes the new score. And what we know is that's how many standard deviations a score is above or below the average, and we usually give them the 2 decimal places. Okay, so what about quartiles and outliers then? Well, Q3, I know the cumulative frequency would be 0.75. 75% would be below Q3. Now, if I was to look that up into our tables, then that is 0.67. So Q3 must be 0.67. That's the answer that would give me 0.75. Now, by symmetry, that means Q1 must be negative 0.67. And so the interquartile range, that's what we're more interested in, is 1.35. Now, what we say is an outlier is 1.5 times the interquartile range above or below, if you go the other way, the Q3 and Q1. So therefore, if I had a z-score of more than 2.7, then I would be considered an outlier of the data. So I'm more than 2.7 deviations away from the average. And obviously, at the other end, it would be negative 0.70. So any outlier where the z-score is outside that range, so less than negative 2.7 or more than 2.7, is an outlier. Now, why are outliers important? Well, when we're looking at the statistics, outliers can really throw your data out. It's an anomaly, and so sometimes we'll just exclude them from the data. So we're waiting for a prescription to be prepared at the pharmacy or the chemist. And we know it's normally distributed with an average of 15 minutes waiting for that script to be filled and a deviation of 2.8 minutes. So let's find the probability that the waiting time will be more than 20 minutes for the script to be filled. So I'll let my random variable be W for waiting time. And they've told me that's normally distributed. The average was 15. And well, they told me the deviation, so the variance is that squared, 7.84. We want to know the probability that W is greater than 20, but we're going to standardize this so we can just look up our table of values and what have you. Now that would be the same as Z is greater than, well, 20 minus the average divided by the deviation. We've got greater than, our table of course does less than, so I want 1 minus, and that works out to be 25 on 14. And so I look up my tables or put it in the calculator, however we're doing it, we end up with almost a 4% chance that you're going to have to wait for more than 20 minutes. The TQ company makes a soft drink sold in 330ml cans. The actual volume of the drink, because they're just using a machine to put the drink in there, they'd get lucky if every single one was always 330ml, but it's normally distributed with a standard deviation of 2.5ml. This company wants to ensure that at least 99% of the cans contain more than 330. People aren't going to complain if there's more than 330, they'll complain if there's less. So we've got at least 99% of the cans more than, well, okay, we're going to be happy. So the machine, we've got to set it on some volume to put in there. What volume should we set it at so we can do that? V is going to be the volume of the drink. Normally distributed, the average is what we're going to set the machine at to deliver at. That's what we're trying to work out. And the deviation they've told us is 2.5, which means the variance is 6.25. So we want to know the probability that the volume is greater than 330. Now 330 minus the number we're looking for divided by 2.5. We're saying that this has to be 0.01, because again, we want a 99% chance that it's above that, so a 1% chance that it's below. So we need to look up in our table what gives the answer of 0.01, but of course our tables won't tell us that because it only gives us positive numbers. You've got to remember it's a negative. Let's look it up and we get 2.33. Just got to work out this equation. Now what is mu? And it works out to be 335. So alright, if they set it at 366ml, then 99% of their cans should have more than the 330 that the label on the can says. Biologists been collecting data, as biologists do, a particular species of cactus. They've observed that 34.2% of the cacti are below 12 centimetres in height, and 18.4% are above 16 centimetres in height. Assuming that those heights are normally distributed, what is the mean and the deviation of this distribution? H is going to be my height of the cactus, and this time I don't know either piece of the important information. We're trying to find both of them. We want the probability that, and if I standardise the data now, that 12, that's what we're looking for, below 12, but standardise it, subtract the average, divided by the deviation, is 3.42. So the first one's 0.342, the second one's 0.184. Okay, we look up our table, we say, well, when is this 0.342? And again, that's the one's below, and the other one 0.816, at least that one we can read straight off our table, we can look at that one. Again, we just go through, find the appropriate number or the closest to it that we can find, and we'll come up with, right, the first one, negative 0.41, and the second one, 0.9. I now have two equations, two pronumerals that I want to find, simultaneous equations. We should be able to find our answer. And nicely, they're both minus mu, so that'll cancel. And we get, okay, there's a deviation of 3.05. Sub it back in, we get an average of 13.25. Okay, so 16E, 16F, playing with standardising the data.